Okay, our last lecture of this unit and for the semester is talking about kinetics. Kinetics deals with how fast a reaction occurs. There are different things that you can do to change how fast a reaction occurs. You can increase your temperature. If you think about it, it's easier to dissolve sugar in hot tea than it is in cold tea. Concentration, by changing how much sugar you put in there, that changes how concentrated it is. We'll deal with concentration in the iodine clock reaction lab. Particle size, if you think, still dealing with sugar. If you have a packet of sugar, it dissolves faster than if you have cubed sugar. Catalysts and inhibitors. A catalyst is something that will speed up a reaction, and an inhibitor slows it down. Some of you probably use inhibitors all the time and you don't even realize it. For example, when you put lemon juice on apple slices to keep them from browning, you're inhibiting that oxidation reaction from occurring. We need to know how to graph reaction rates. So this is an example of a graph. You've got your reactants. Your E sub A is energy of activation. That's how much energy does it take to get the reaction started, and then you have your products down here. This particular reaction is a exothermic reaction because your products are at a lower energy level than your reactants started out at. If we were doing an endothermic reaction, it would look something like this, where your products ended up, and then you have your reactants over here, at a higher energy level. I mean, you've had to put more energy into it to cause a reaction to occur. And you can see here that how much energy is involved without a catalyst. This is the energy involved with a catalyst, and then an inhibitor would have it coming up here. You still end up in the same starting spot and ending spot, but your actual initial energy is there. At the top of the hill, so to speak, that's your activated complex. That's where it's neither a reactant or a product, and you saw this in the gizmo, the collision theory gizmo, showed you your activated complex as things were coming together and then breaking apart. Okay, we're going to talk about rate laws. Your rate law can only be determined through experiments. Only the reactants are involved, because you're dealing with how fast does a reaction occur. The subscripts, your X and Y up here, those are your reaction orders. K is your constant, and we're going to do a calculation so that you can find what your X and Y, actually I'll do X, Y, and Z, of a reaction is. So you want to pause me and write all of this information down so that on the next slide you'll understand what's going on as I work the problem. So take a moment to write everything down. Okay, so hopefully you've copied down the table, and so we're going to work out the problem. What you're doing is you're going to find out exactly what the rate law is. So it's going to end up being your rate is equal to your constant times your BrO3 raised to some power, your Br minus raised to a different power, and your H plus raised to an even different power. So the way we do that is we compare experiments. You'll notice from the table that some experiments the concentrations remain the same and some of them changed. So the first thing I'm going to do is I'm going to try and find out what BrO3, I'm going to find out what X is. So I'm going to compare experiment number 2 to experiment number 1. And I just plug in to this general formula what it is. So the rate of experiment number 2 is 1.6 times 10 to the negative 3. K is a constant So BrO3 was a 0.2, and that's to the X. Br minus was 0.1, that's to the Y. And the H plus was also 0.1. So we have 8.4 times 10 to the negative 4. Okay, that's 0.1 to the X, 0.1 to the Y, 0.1 to the Z. So you can see that I can cancel out my K's. It's going to be the same. I can cancel out my 0.1s to the Y and my 0.1 to the Z, because those are identical to each other. So now I'm just left with a ratio to work with. So when we do the math on the right side, we get 1.9, and then 0.2 divided by 0.1 is 2 to the X. So your X is approximately 1, because you're basically saying 2 equals 2 to something, and the only way that could be equal to each other is if it is 1. So we now know that this is a 1 up here. Okay, so then we compare another set of data. So 3 over 2 gives us 3.2 times 10 to the negative 3 over 1.6 times 10 to the negative 3. Our K's are going to be there. So we have 0.2 to the first, 0.2 to the first, 0.2 to the Y, over 0.1 to the Y, and we're still able to cancel out our unknown Z's. So canceling out, those cancel out. Your 0.2 to the first cancels out, but even if they didn't cancel out, you would be able to do that math. But when we do this math, we get 2 equals 2 to the Y, so Y equals 1. That's a 1 there. Okay, and to find the last set of, or to find Z, let's go back to the color I was using. If I compare experiment 4 to 1, that means we have 3.2 times 10 to the negative 3 over 8.4 times 10 to the negative 4. So 0.1 to the first, another 0.1 to the first, then we have 0.2 to the Z over 0.1 to the Z. And when we cancel out our like terms so that we're making it a simple math problem, we get 3.8 equals 2 to the Z. So 3.8 is basically 4. And so 2 raised to the power equaling 4, that means that our Z has to be 2. So the Z over here is a 2. So our rate is K BrO3 to the first, Br minus to the first, and H plus to the second. So at this point you could pick any experiment, plug the numbers in, and we could find out what K is. And we'll do some practice problems like that in class. When I asked what is the reaction order, well, it's reaction order to first for BrO3. Br minus is also to the first. H plus is a second order reaction. Overall, the overall order is 4 because you add up all of those superscripts to find out your overall rate order.